Welcome, fellow curious minds, to the deep dive. Now, you're likely familiar with high-pressure die casting. It's pretty critical for so many precision parts, right?
Yes.
Think medical, marine, telecoms, that sort of thing. But even here, in this really advanced field, there are these hidden challenges lurking. So today, we're pulling back the curtain. We want to expose two of these sort of silent saboteurs, gas porosity and shrinkage porosity. We'll dig into what causes them, but maybe more importantly, how engineers can actually see these invisible threats and, design them out often before a single part even gets cast.
Yeah, it's quite remarkable, isn't it? Because these defects, they might look like just random imperfections, but really they're signals, potent signals. And understanding those signals lets engineers move from just reacting, fixing problems after they happen, to proactively preventing failures, which in precision manufacturing, that's just invaluable.
Okay, so we're diving into the challenges of high-pressure die casting. A process picked specifically for its amazing efficiency is precision, making those really critical aluminum parts. You mentioned medical gear, vital marine electronics, the components driving our global telecom networks. These aren't just standard parts, are they? Lives, critical operations, they can literally hinge on them performing flawlessly.
Right. And if you zoom out a bit, that very efficiency and precision, well, it makes die casting powerful, but it also inherently raises the stakes when defects do pop up. The real trick, the challenge, is making sure efficiency doesn't undercut quality, especially like you said, when these parts are going into such incredibly demanding uses.
Okay, let's tackle gas porosity first.
Yeah.
What exactly are we talking about here? I mean, porosity at its core just means a void, right? A little pocket where solid metal should be, but
Yeah.
it isn't. And with gas porosity specifically, that pocket is full of trapped gas.
Exactly. Could be just plain air, could be superheated steam, maybe even vaporized lubricant that got kind of sealed inside when the metal solidified.
And what's interesting, you mentioned how they look.
Yeah, what's intriguing is they're typically quite round, smooth inside, almost like tiny little balloons trapped in the metal. And sometimes you just won't see them at first glance. They're completely hidden. It's only later, maybe after machining or pressure testing or applying a coating,
Oh,
that suddenly you see blisters or the part starts leaking. That's often the hidden gas pockets finally showing themselves, ruining a part that looked totally fine initially.
right. Okay, so here's where it gets really interesting for me. How does this gas get trapped? You mentioned three main ways.
Yeah, basically three main culprits.
First, trapped air. How does that happen with molten metal?
Well, think about the speed. Molten aluminum rushes into that mold cavity incredibly fast, like 100 to 300 kilometers per hour. It's got to push the air that's already in there out of the way. But if the mold's venting the escape path for that air isn't perfectly optimized,
Some gets left behind.
exactly. Some air gets compressed, trapped as bubbles. Simple as that, but hard to avoid sometimes.
Okay, and the second one, steam from moisture.
Yeah, it's amazing how little moisture it takes. Could be from the release agent not being totally dry, maybe condensation on the cool mold surface, even slightly wet tooling. The second it hits that super hot molten aluminum, it flashes instantly into steam.
And expands rapidly.
Massively expands, creates these unexpected gas pockets.
And the third culprit, something about lubricant.
Right, burned lubricant. So
Uh-huh.
every release agent, the stuff used to help get the part out of the mold, it contains hydrocarbons. Now, if you put too much on or apply it unevenly, under that intense heat, it just vaporizes, burns off, basically, and forms even more gas right there inside the cavity.
Huh. So something meant to help can actually cause a defect.
Precisely. It's a fine balance.
So fixing this
Mm-hmm.
sounds like it needs tight control.
You've hit the nail on the head. It always, always boils down to one word: control. We have to meticulously control the melt quality first. Make sure the aluminum is dry, properly degassed, handled carefully. Then we control the shot profile, that's the speed and pressure curve, as the metal injects. We want to actively avoid turbulence, which can drag air into the flow.
Smooth flow is key.
Absolutely critical. Smooth laminar flow where the liquid moves in parallel layers, no churning. And of course, we rigorously control the venting, designing those vents carefully, placing them correctly so trapped gases have a clear exit route. And yes, controlling the release agent. Minimal amount, applied consistently, fully dried before every single shot.
Okay. And for the really critical stuff, like those medical parts or telecom seals, you mentioned something extra.
Ah, yes. For the absolute highest integrity parts, they often use what's called vacuum assist. They literally pull a vacuum in the mold cavity right before injecting the metal.
Sucking the air out.
Pretty much. It drastically reduces any residual air, slashing the risk of gas porosity almost to zero. It really shows the lengths engineers go to, doesn't it, to guarantee performance.
But I guess that vacuum assist, does that add significant cost
Yeah.
or complexity? Is it used everywhere or just for those high-end applications?
That's a really good point. Vacuum assist is incredibly effective, no doubt. But yes, it definitely adds complexity to the tooling, to the machine setup, and yeah, it adds cost. So while it's a fantastic tool for those critical, high-value parts where failure just isn't an option, you're right. It's often not economically practical for every single component. It's always that trade-off, isn't it? Performance versus cost.
Makes sense. Okay, let's shift gears. Let's talk about the other type. Shrinkage porosity. You said this one's different. Not trapped gas, but missing metal.
That's right. It's fundamentally about a lack of material in a specific spot.
So why does metal just disappear? What's the mechanism there?
Okay, think about what happens when metal cools. Any metal, really. As aluminum goes from liquid to solid, it shrinks. It takes up less space. That's just basic physics, basic material science.
Okay, it shrinks.
Right. Now, imagine you have a part with a thick section, like a boss, or just a heavy area somewhere in the design. The outer surfaces of the part, they cool and solidify first because they're touching the cooler die steel, but that thick center, it stays molten, hotter for longer. We call these areas hot spots.
Because they hold the heat?
Exactly. They trap heat longer than the surrounding areas. Now, if there's no way for extra molten metal to flow into that hot spot as it finally cools and shrinks, the metal in the center essentially just pulls away from itself as it solidifies under constraint. And that leaves behind an internal void, a cavity. That is shrinkage porosity.
Oh, okay. So it's like a little vacuum created by the shrinking metal itself if it can't get fed more liquid.
That's a great way to think about it, yes. It's a void created by volume loss during solidification.
And you mentioned these look different from gas pockets.
They do. Unlike the usually smooth, round gas pores, shrinkage voids are often irregular. They can be jagged, rough-surfaced, almost like little internal tears or caves in the metal. You typically find them in those thick sections we talked about, or where there's a sudden jump from a thin wall to a thick wall, or even in sharp internal corners that act like heat traps.
So these hot spots sound like they're almost inevitable with complex shapes. Are there common design mistakes that make them worse? Things engineers might miss?
Oh, absolutely. The classic ones are those abrupt changes in wall thickness. Imagine going from, say, 2 millimeters thick straight to 10 millimeters thick with no transition. That junction is a prime spot. Sharp internal corners are another big one. They just don't cool efficiently. These areas solidify last, and if they're kind of isolated from the main flow path of molten metal during that final stage, boom, high risk of shrinkage. It's like you're fighting against the natural way heat wants to flow or doesn't want to flow in the part.
Okay, so how do you fix that?
I see.
It sounds like less about controlling gas and more about controlling cooling.
Exactly. The fix for shrinkage isn't just tweaking the process parameters, though that helps. It really starts much earlier. It's fundamentally about designing solidification pathways.
Okay.
Right from the very beginning, in the part design and the tool design.
Solidification pathways, what does that mean in practice?
It means we try to encourage what's called directional solidification. We want the part to freeze progressively, predictably, usually from the thinnest sections furthest from the gate, back towards the thicker sections near where the metal enters. This way, there's always a path for liquid metal to feed those areas that are solidifying last and shrinking.
How do you encourage that?
Several ways. We optimize the cooling channels inside the die itself, placing them strategically to pull heat out in a controlled manner. We might position overflow wells, extra pockets, to draw metal and heat near potential hotspots. Or we can use something called squeeze pins. These are like little hydraulic cylinders built into the die that apply localized pressure right on those heavy sections as they solidify, forcing metal in.
Ah, like giving it an extra push where it needs it.
Precisely. And we also fine-tune the process parameters like intensification pressure, that's extra pressure applied after the mold is full, and the holding time for that pressure. Keeping that squeeze on the molten metal during that critical shrinkage phase helps tremendously to feed those voids.
It sounds like a lot of this comes back to the initial design, though, working with the customer early on.
Yes, absolutely. That's often the most effective fix. Working closely with the customer during the part design review, looking at wall thicknesses, smoothing out those sudden transitions, adding generous radii to sharp corners. Sometimes a simple design tweak, like maybe coring out a thick boss to make it hollow instead of solid, or just adding a fillet, can dramatically reduce the tendency for shrinkage porosity, making it much easier to manage in production.
So it seems like the best fix happens way before you even make the first part. Prevention at the design stage.
That's exactly it. The most elegant solutions, the most cost-effective ones, often happen right there on the drawing board or, the CAD screen these days. By collaborating early, you can often design out the conditions that cause these hotspots in the first place, rather than just fighting them later on the shop floor. It's proactive versus reactive, and it saves a huge amount of time, effort, and potential scrap down the line.
So stepping back a bit, the big picture here seems to be that these defects, gas and shrinkage porosity, they aren't just random bad luck.
Not at all. They're signals. They're clues telling you something about the design or the process.
And while they're definitely challenging for engineers,
They are among the most challenging, yes.
they're also, maybe surprisingly, quite controllable if you approach them with the right knowledge and discipline.
Extremely controllable. That's the powerful part. If you understand the underlying physics, the root causes, you can address them systematically through thoughtful design, like we just discussed, and through really stable, well-understood process control right from the very beginning. That's the key.
So what's the takeaway for you, our listener, in all this? I guess it's about recognizing that real knowledge isn't just about spotting a problem, like seeing a void in a part. It's about digging deeper, understanding the why behind it, the intricate root causes, and then, ideally, using that understanding to design the problem out of existence entirely. It's that deeper level of insight, isn't it, that really makes you well-informed. Well, we hope this deep dive into the maybe surprisingly fascinating world of die-casting porosity has given you some valuable insights, maybe even a few of those aha moments. It really is a testament to how complex even seemingly straightforward manufacturing can be and just how critical that detailed engineering knowledge really is.
And it does raise an interesting question for you to think about, doesn't it? This principle we've been discussing, designing out defects, focusing on prevention rather than just fixing things after they break. How might that apply elsewhere, in other areas of your life or your work? Think about where proactive prevention, based on really understanding the root causes, could make a significant difference, maybe somewhere completely unexpected.
That's a great thought to end on. And that's it for this deep dive. Thank you so much for joining us. Until next time, keep digging deeper into the knowledge that matters.